Look at the device you are watching this on. Inside it are not one but many semiconductors, processors, memory, power controllers, wireless chips, sensors. They were not all made in one country, but the most advanced processor among them may depend on a chain so concentrated that only a handful of companies can complete it. More than 90% of the world's leading-edge chips are manufactured in Taiwan. The machines required to print their smallest features come from one Dutch company. Much of the design value begins in the United States. Several materials underneath the process are heavily concentrated in China. No country controls the entire chain. Every major power controls a piece. Every major power depends on the pieces controlled by someone else. That is the real danger. The modern world did not place its future inside one monopoly. It divided that future among a series of choke points and then allowed rivalry to grow between them. So this episode is not simply about why the world depends on Taiwan. It is about how specialization created that dependence, why money alone cannot remove it, and what happens when governments try. This is the chip war. Before we follow the conflict, we need to understand the object at its center. In 2025, worldwide semiconductor sales reached almost $800 billion. Industry projections place 2026 near $1 trillion. Yet even that figure understates the industry's reach, because semiconductor revenue measures the component market, not the economic activity of every product and service those components enable. That is not the value of phones, computers, cars, cloud services, or artificial intelligence. It is the value of the chips before most consumers ever see them. And chips are not one market. The word covers everything from inexpensive controllers inside household appliances to the leading-edge logic used for AI and high-performance computing. A chip does not become unimportant simply because its transistors are larger. During a disruption, a missing power management chip can stop completion of a processor worth many times more. This distinction matters because concentration is not equal across the industry. Taiwan does not manufacture 60% of every chip on Earth. It accounts for more than 60% of global foundry revenue, the business of manufacturing chips designed by other companies. At the leading edge, however, the concentration becomes much more severe. US trade officials estimate that Taiwan accounts for more than 90% of leading-edge chip manufacturing. That small category carries extraordinary strategic weight. The most advanced nodes power flagship smartphones, data centers, and many of the systems driving the AI investment boom. Mature nodes carry a different kind of power. They are embedded across vehicles, factories, and infrastructure, often in products designed years earlier and difficult to qualify around a replacement. A reasonable response would be, if these chips matter so much, why not manufacture them in many places? The answer is not that governments failed to notice a simple solution. It is that the semiconductor industry became powerful by doing the opposite, dividing impossible problems among specialists. One company could focus on processor architecture, another could perfect lithography, another could refine a manufacturing process across hundreds of products, another could specialize in memory or packaging. The same specialization that made chips improve so quickly also made the supply chain difficult to duplicate. To see how, we have to return to a decision made in Taiwan in 1987. For much of the industry's early history, leading semiconductor companies were integrated. They designed chips and manufactured them inside their own factories. Intel and other American firms became symbols of that model. Design knowledge, process technology, and production lived inside the same organization. But semiconductor fabs became more expensive with every generation. A company could design an excellent chip and still fail because it could not afford the factory needed to manufacture it at scale. Worse, a fab begins losing economic value if it sits underused. The equipment is enormously expensive, the technology ages quickly, and profitable operation requires a steady stream of wafers. Morris Chang saw an opportunity inside that problem. After a long career in the American semiconductor industry, Chang helped establish Taiwan Semiconductor Manufacturing Company, TSMC, in 1987. Its proposition was radical in its simplicity. TSMC would manufacture chips for other companies while avoiding products that competed directly with its customers. It was not merely renting factory space, it was offering trust. A design company could give its most valuable intellectual property to TSMC without expecting the manufacturer to release a rival chip. That separation changed the economics of the industry. New companies no longer needed to finance a leading-edge fab before selling their first processor. They could concentrate capital and talent on design, then purchase manufacturing capacity from a specialist. The risk of filling a factory could be spread across many customers rather than carried by one product line. This helped create the fabless model behind companies such as Nvidia, AMD, and Qualcomm. Apple could design processors around its own devices without building the factories that produced them. TSMC, meanwhile, served hundreds of customers. Every new product gave it more manufacturing experience. Every process improvement attracted more demand. More demand justified more investment in the next node. When one customer's demand weakened, capacity could eventually serve another. When a process problem appeared across products, the lesson could improve the platform used by many customers. A feedback loop emerged. Scale produced better yields. Better yields attracted customers. Customers financed even greater scale. By 2025, TSMC reported manufacturing more than 12,000 products for 534 customers. Technologies at 7 nanometers and below generated 74% of its wafer revenue. That customer diversity matters. TSMC can invest for a market larger than any single chip designer could guarantee on its own. This was not an accidental factory that happened to become large. It was a system for compounding processed knowledge across decades. A semiconductor process is not complete when the equipment is installed. It becomes commercially valuable when engineers can produce acceptable chips repeatedly at high yield, while controlling thousands of variables across an entire production line. And that reveals the first twist in this story. The world depends on Taiwan, not because every other country forgot how to build a factory. It depends on Taiwan because TSMC accumulated a combination of scale, supplier coordination, yield knowledge, and customer trust that a new building cannot instantly reproduce. But even TSMC is not self-sufficient. Its most advanced fabs depend on a second choke point located almost 9,000 kilometers away. The smallest features on leading-edge chips are patterned with extreme ultraviolet lithography, EUV. EUV is not simply a better camera. It is an industrial system built to generate, control, and direct light that is exceptionally difficult to produce and absorb. Ordinary lenses cannot handle this wavelength in the usual way, so the system relies on specialized reflective optics and an extreme vacuum environment. Each exposure is one step inside a manufacturing crossing sequence that may repeat layer after layer across a wafer. The engineering required components and expertise from a global supplier network. The light source, mirrors, stages, sensors, control software, and contamination management each represent a field of engineering deep enough to become its own industry. Yet only one company integrates them into production-ready EUV lithography systems. That company is ASML in the Netherlands. In 2025, ASML shipped 48 EUV systems. Compare that with the scale of the industry they support. Hundreds of billions of dollars in annual chip sales, enabled in part by a few dozen new machines. There are two important corrections to the usual viral version of this story. First, not every chip requires EUV. Mature node chips used in vehicles, industrial equipment and appliances often rely on older lithography technologies. Second, not every EUV system costs $400 million. Conventional EUV systems are generally less expensive. The newest high-NA generation reaches the range commonly associated with that figure. The monopoly is still real. ASML is the sole supplier of EUV lithography systems, but the strategic fact is more precise than one machine makes every chip. The fact is this: manufacturers pursuing the smallest features at commercial scale depend on a tool chain that no rival supplier currently offers. A competitor would not only have to reproduce the machine, it would need to reproduce the supplier network, service organization, installed knowledge and confidence of customers whose factories cannot afford prolonged downtime. ASML itself also depends on specialized suppliers. Its success does not eliminate the network, it concentrates responsibility for integrating the network. Now the map becomes clearer. American firms hold enormous strength in chip design. ASML supplies EUV lithography from the Netherlands. Taiwan and South Korea concentrate advanced fabrication, memory, and packaging capabilities. China leads production of several minerals and processed materials used across advanced manufacturing. This is not a four-card house in which removing any card instantly ends all semiconductor production. Different chip categories have different dependencies, inventories, and substitutes. But at the leading edge, replacing a missing node can take years rather than weeks. That delay is what turns commercial concentration into national security risk. And nowhere is that risk more politically sensitive than Taiwan. The phrase "silicon shield" describes a powerful idea. Because the world depends on Taiwan's semiconductor production, every major economy has an interest in preventing disruption there. A crisis around the island would not remain local. It could interrupt leading-edge production used by companies and institutions across the United States, China, Europe, Japan, and many other markets. Inventory could soften the first shock for some products, and older fabs elsewhere would continue operating. But a mature node factory cannot simply begin producing a leading-edge design. The design, process, and production line are inseparable. In that theory, dependence becomes deterrence. The economic cost of instability becomes one more reason to preserve the status quo. But this is a theory, not a proven guarantee of peace. Economic interdependence can raise the price of conflict without making conflict impossible. It can also create pressure for every side to reduce its dependence before a crisis occurs. That produces a paradox. The more valuable Taiwan's semiconductor position becomes, the stronger its economic importance appears. But the more governments fear that concentration, the more money they spend building alternatives elsewhere. If diversification succeeds, Taiwan may become less indispensable. If it fails, the original vulnerability remains. And partial success creates a more complicated result. The world gains backup capacity, while still depending on Taiwan for the density of expertise and suppliers surrounding its most advanced production. So the silicon shield contains two competing processes: dependence reinforcing the status quo and fear of dependence slowly eroding it. The United States responded to that tension with two different strategies, one designed to build and another designed to deny. The first strategy was industrial policy. The CHIPS and Science Act created a semiconductor program worth roughly $52 billion, including $39 billion in manufacturing incentives. Its goal was not to manufacture every chip domestically. It was to increase US capacity, attract private investment, and restore production of technologies considered strategically important. The incentives also recognized a basic problem. If domestic production is structurally more expensive, national security value will not appear automatically on a private company's balance sheet. Government is being asked to pay for resilience that the market previously treated as duplication. The second strategy was export control. Beginning in 2022 and updated afterward, the United States restricted access to certain advanced computing chips and semiconductor manufacturing equipment for China and other controlled destinations and end uses. The stated objective was national security, limiting access to technologies that could support advanced AI and military systems. The Netherlands also imposed licensing restrictions affecting exports of some advanced lithography equipment. That mattered because US controls alone could not close a choke point owned by a Dutch company. Here is the second major twist. A supply chain created by globalization can only be restricted through cooperation among the countries that control its separate tools. A restriction with a large loophole may redirect purchases instead of denying capability. A restriction made too broad may also damage firms in partner countries whose cooperation makes it effective. No single government can regulate the complete chain because no single government owns it. China responded by accelerating domestic investment. A major semiconductor fund announced in 2024 was valued at roughly $47.5 billion. Chinese firms also demonstrated that controls are barriers, not time machines. Huawei's Mate 60 Pro incorporated a 7-nanometer class chip manufactured by SMIC using a process that did not depend on imported EUV equipment. That result did not erase the technology gap. Producing advanced chips through older tools can require additional process steps, create yield challenges, and increase cost. But it showed that export controls may slow progress without freezing it permanently. They can also strengthen the political case for investing in substitutes. Their effect must therefore be judged over time, not only by what they prevent today, but by whether they delay capability longer than they accelerate the search for alternatives. China possesses leverage of its own in critical materials. According to the US Geological Survey, China accounted for approximately 98% of primary refined gallium production, 85% of silicon metal, 83% of mined tungsten, and 68% of mined of rare earths in the underlying June 2023 global data. These shares reflect years of processing capacity, industrial scale and cost competition, not simply the location of mineral deposits. Those are different markets with different substitutes and different relevance to semiconductor manufacturing. They should not be compressed into the false claim that China controls 99% of every critical material. The strategic pattern, however, is clear. China has imposed export controls on several critical minerals, creating another form of bargaining power inside the wider technology system. The chip war is therefore not a clean contest between one producer and one customer. It is a network in which each participant holds leverage in one area and vulnerability in another, and using that leverage carries a cost. When US export controls were announced in October 2022, major American chip stocks lost more than $100 billion in market value over a short period. That was an investor reaction, not cash physically transferred out of those companies. But the reaction exposed the commercial dilemma. China was simultaneously a strategic competitor, a major customer, and a manufacturing center embedded across the electronics industry. Revenue earned in that market could support research by American serfs. Restricting sales could protect a commercial scale while also reducing some of the commerce generation. Restrictions can deny capability. They can also reduce sales, encourage substitution, duplicate investment, and raise costs for allied firms. That does not prove the controls are right or wrong. It means their effects cannot be measured only by what the target loses. A serious accounting must include what the controlling countries pay as well. This is why the chip war cannot be won simply by closing a gate. The deeper strategy is to build another road. The most visible new road is in Arizona. TSMC's original $12 billion US plan expanded dramatically. By 2026, the company described a planned investment of up to $165 billion around its Arizona cluster. Its first Arizona fab entered volume production using N4 technology. A third fab, begun in 2025, is planned for N2 and A16 class processes. The cluster is therefore more than a symbolic backup plant. It is a long-term attempt to establish an advanced manufacturing base around which suppliers and skills can accumulate. That change is an important claim often repeated about reshoring. It is no longer accurate to say the United States is receiving only yesterday's technology, while every leading-edge process remains permanently in Taiwan. TSMC is preparing advanced production in the United States. At the same time, its 2025 annual report says it is building multiple phases of 2-nanometer fabs in Hsinchu and Kaohsiung and continuing major advanced packaging investment in Taiwan. Diversification is occurring, duplication is not complete. And the factory building is only one layer. An advanced fab needs equipment, ultra-pure materials, reliable power and water, process engineers, maintenance teams, and a supplier ecosystem capable of solving failures quickly. It also needs customers willing to redesign or qualify products for that specific process, and enough demand to keep extraordinarily expensive production lines utilized. Then the finished wafer must be cut, packaged, and connected to memory. For AI accelerators, advanced packaging, such as TSMC's CoWoS and high-bandwidth memory, became additional constraints. The 2026 capacity for some of those products was committed before the capacity physically existed. Removing one bottleneck revealed the next. An AI accelerator is not useful merely because its logic wafer exists. It must be combined with memory and packaged at the required performance, thermal and power limits. This is why a fab announcement and a resilient supply chain are not the same thing. Capital can finance a building. It can purchase equipment when equipment is available, but process yield depends on accumulated learning, and supplier coordination depends on relationships developed through repeated production, even two uptime using similar equipment, because uptime, defect control, cycle, determine how many and engineering response, how many usable chips leave the line. The world can build more geographic redundancy. It is already doing so in the United States, Japan, Europe, and elsewhere. What it cannot do quickly is recreate every layer of the most advanced ecosystem inside each national border. That leads to the verdict hidden beneath the entire chip war. The obvious interpretation of this story is that Taiwan controls the future. The more accurate interpretation is that Taiwan controls one exceptionally important section of a system that no participant controls alone. TSMC depends on ASML and hundreds of equipment and material suppliers. Fabless American companies depend on foundries and packaging. ASML depends on a global supplier network. China holds strength in manufacturing scale and critical materials while remaining constrained in parts of the leading-edge tool chain. The system is concentrated because specialization worked. It reduced duplication, spread research costs across customers, and allowed each part of the chain to become extraordinarily capable. Consumers received faster and cheaper computing, partly because every country did not attempt to build a complete duplicate of every layer. The political objective now is to make that system less fragile without destroying the cooperation that made it productive. That is much harder than bringing chip-making home. Home is not one factory. Home would have to include the tools, materials, engineers, packaging, memory, energy, suppliers, and decades of process learning around it. The United States can reduce its exposure. China can build alternatives. Europe can defend its equipment advantage. Taiwan can spread capacity while preserving its most mature ecosystem. But for the foreseeable future, none can achieve full independence without accepting enormous cost and, potentially, slower innovation. A fully national supply chain might sound secure, yet it could be weaker if it operates at lower scale, learns more slowly, or loses access to the best external tools. So the chip war is not a race to own every link. It is a race to decide which dependencies are tolerable, which are dangerous, and who will pay to duplicate them. The winner may not be the country that manufactures everything. It may be the country, or alliance, that can survive the loss of one choke point without losing access to all the others. That requires redundancy at selected points, trusted partners at others, and enough transparency to recognize a bottleneck before it becomes a crisis. That is why the world still depends on one island, not because Taiwan possesses magic and not because everyone else was asleep. It is because 40 years of specialization concentrated knowledge, faster than politics, could distribute risk. Governments are now trying to reverse that risk without reversing the progress. Whether they can do both is the real chip war. Chips reveal a larger rule about economic power. Hosting a factory is not the same as controlling the valuable knowledge around it. That distinction matters far beyond Taiwan. Across Asia, global companies are moving production, assembly and suppliers into new locations, and one of the biggest beneficiaries is Vietnam. But Vietnam's rise raises the same question we found inside the chip industry. When factories move into a country, how much power moves with them? That is the next file on the Rise Index. Subscribe if you want to see the hidden systems behind the headlines, not as a contest of slogans, but as a map of incentives, constraints and power. This is the Rise Index, and the map is only beginning to move. Thank you for watching all the way to the end. If this changed how you see the map of power, subscribe to the Rise Index and follow along, because the next shift is already beginning to move.